A lot of storm chasers know how to pull up model data, but far fewer know how to use it correctly. Looking at the wrong models at the wrong time can completely derail your forecast. In this episode, we're walking through the forecast timeline and discussing which models you should be using several days out, 2 days out, and the morning of the event. Understanding this progression is one of the biggest steps towards becoming a better forecaster. I'm Gabriel Harbor, host of the Storm Chaser Coaching Podcast, and I'm joined today by Lead Coach Trey Greenwood. Trey, how you doing?
Doing well. Excited to talk about models. I think that's a big sticking point for a lot of forecasters and chasers. So this should be a good one.
Completely agree. And before we get into the questions, I want to remind folks that we do have a link you can click in the description below to get access to the cheat sheet for this episode. It's our collection of notes that we use to create the outlines for these. And if you fill out the form, you'll get access to not only this episode, but to every episode that's ever been recorded and will be recorded in the future. You can use those however you would like, as refreshers, as information for any future projects you're working on, etc. Link in the description below. Question one, Trey. Why is it dangerous to rely on long-range deterministic models when forecasting severe weather? And I should probably add the caveat as well. What the heck is a deterministic model? That's a big word that I don't think a lot of people are familiar with.
So deterministic models are basically just your individual runs of a given model. For example, your European model or the GFS model. Just if you're looking at one run of those, the operational run of the GFS or the European model, or any model for that matter, that is the deterministic model. Ensemble models, which we'll talk about here in just a second, they take into account slightly different initial conditions for those model runs and then bring those all together as a whole. And then we can average out if a particular member is wonky or whatnot, that can average those out. Long range models tend to have a lot more error in them. The atmosphere is a very complex system, as we all know. There's a lot of very complicated equations and whatnot that govern the atmosphere. And several days out, obviously, we don't have the observed data that we need to feed those models that is more accurate. The model's basically just guessing what's going to happen down the road, and errors tend to multiply and become much more noticeable the farther out you go from a particular event. So if you're looking at a single deterministic model 7, 8, 9 days out, it's probably not going to be what ends up happening. In fact, it might be drastically different than what ends up happening. So you really need to use those deterministic models with extreme caution. We can get into some more about ensembles here, but those are going to be your better ones to use. But using long-range deterministic models, that's usually going to have a lot of error in them, especially the farther out from an event you go.
So, how should ensemble models, which are, I wouldn't say the opposite, but definitely qualitatively different than the deterministic models, how should they be used when you're 3 to 4 days out from a potential event?
Yeah, so as we said, ensemble models basically take the model that you have. So let's say the GFS model, the American Medium Range model. You take the GFS model, you run it a bunch of different times with slightly different initial conditions to get a bunch of different model outputs. An ensemble puts those all together, and then we can average those out. So we can get the average 500 millibar pattern going out in time. We can get the average moisture, average surface dew points going out in time. Rather than just taking one model at face value, we're combining them into a holistic view, and that allows us to weed out some of the wonkier model runs. Say if one particular ensemble member is way off from the others, we're averaging them all those ensemble members out so we can weed out the wonky runs. This is a lot better to use than those deterministic models because we're averaging things out and we're not just taking one specific run at face value. So once you're 3, 4, 5 days out, you can start looking at the ensemble models just to get a basic idea of the pattern. You're not looking at the ensemble models for specific high resolution details. The surface low is going to be in far northeast Kansas at X time 4 days out, and you're going to have 60 to 62 dew points across this X corridor. That's not what you're looking for with those ensemble models. You're just getting a general sense of the pattern. Are we going to have a deep digging trough? How is the general trough geometry looking? Does it look like more of a negative tilt trough or a positive tilt trough? Are we going to have moisture return in general? We see at least decent moisture up to a general vicinity. You're just trying to get a general idea of if there's going to be severe weather. And then as we get closer to the day of the event, you can start honing in on some of the more specific fine scale details using some of the higher resolution models and observed data.
Before we move on to the next question, I want to let everyone know that we have some awesome ebooks that you can get in the description below. Doesn't matter if you're on YouTube, Spotify, Apple Podcasts, whatever. Those are going to be down there for you to click. Trey did a tremendous job creating those. We've had so many, thousands of people actually, who have downloaded them, enjoyed them, and we want to extend that offer to all of you folks as well. All right, Trey, next question. When do short range models like the NAM become useful in the forecast process?
The models we were talking about before, the GFS, the European model, those are more medium range models. So you're looking at those 3, 4, 5 days out. Once we get into the day or two before the event, or even the morning of the event, that's when the short range models become much more useful. So the NAM, the convection allowing models start to become more important kind of the morning of the event, even though we know that those have some biases and some caveats that need to be taken into account when using those. They're short range models, so you want to use those maybe a day or two out at most. Any farther than that, toward the end of their range, NAM goes out 84 hours, so what, 3.5 days? That starts to get a little bit dicey. You want to try to get a few more runs in before you start looking at those shorter range models. You want to get closer to the event. So maybe a day or two out at most would be the time to use those short range models.
Why is it important to compare multiple models instead of just relying on one?
That is a critical thing because you don't want to take just one model at face value. All the models are trying to get the same thing, but they're slightly different in how they compute these equations that govern the atmosphere and their schemes that handle things like moisture and pressure and stuff like that, and convection even. So you want to look at multiple models at the same time rather than just relying on one. So you can get an idea of the range of outcomes. Of course, the atmosphere is complex, as we've said numerous times. One model is not going to give you the perfect solution. You're going to have to look for a range of outcomes that could happen based on a bunch of models, and you want to see how those models are differing from one another. So say you're looking at the NAM and the GFS and the European model, maybe a day or two out from an event. And the surface low on the NAM is maybe up in Iowa, but the GFS has it way farther south in Kansas, and then the European model's over in Missouri. So you have a big difference in where the surface low is in that case. Or maybe you have the NAM is showing much more meager moisture return, 60s dew points only making it up to the Red River in Texas and Oklahoma in a certain setup. But the GFS has the 60s dew points all the way up into northern Kansas. Those are big differences, and that is model disagreement. To have a good confidence in your forecast, you want to see the models, which again have slightly different ways they compute these. You want to see those models have a similar looking solution so that you can have higher confidence in what might happen. If you see a lot of disagreement among the models, among the positioning of the surface features or the geometry of the trough, then you're going to have a much lower confidence forecast, and it might be a little bit more difficult to ascertain what might happen in an event.
Lastly, what types of atmospheric features should storm chasers analyze across different model levels?
Usually, you're going to want to look for your 500 millibar pattern, your surface moisture and dew point, and you can look at basically everything you would use to make a forecast. So you could look at all those different upper air levels, 500 millibars being the most important. You can look at 300 millibars for diffluence aloft, 700 millibars for short waves, 850 millibars for the low level jet, surface for, of course, the surface features and the moisture. And that's going to vary among the models. And you can use convection allowing models as well, like the HRRR or the 3 kilometer NAM, for example. Those actually are able to resolve convective elements like storms. So we can get a general idea of what the radar might look like later on in an event. Those have a lot of biases with them, so you should take them with a grain of salt and only really use them the day of the event at most. But we can actually start to pick out what the radar might look like later on in an event using those convection allowing models. And that's pretty much the main usage for those. As far as your other models go, the NAM, GFS, and European model, it's going to be the typical forecasting variables like your upper air pattern, your low level features, your surface features, and stuff like that. You can also look for things like instability, CAPE, things like wind shear, etc. Those can be looked at on the models as well. And pretty much all models will have those. But those higher resolution models, like the convection allowing models, can actually pinpoint convective elements, so you can use those for getting an idea of what might happen as far as the convective evolution in a given setup. Your main models is going to be for the main sort of upper air surface and those kind of features.
This has been excellent. Now, the next time somebody asks you what you think of the 4,000-hour GFS run and whether or not that surface low is going to be in that exact spot in northeast Kansas, you will know exactly how to process that information. It's good wisdom to drop on us here, Trey.
Yep, that is something you see a lot, is a lot of postings of the GFS 300 hours out. as we talked about today, that's going to be something that's not good for forecasting because those longer range models just are not going to be very good until you get closer to the event.
Remember to check out those links in the description below, and then watch another video.